So in the previous video we talked about expressing the algorithm performance as a function of input cells, and we distinguished between the worst case, the best case, and the average case. Okay? So now let's talk about few notations that we would require for the algorithm analysis. And to begin with, we will talk about the theta notation. Okay, so let's consider a function gn. So it's a function with n as the input, and then we are going to define a set which is theta gn. Okay, so this set will include all the functions fn such that there is some condition which we have to meet. Okay, so we have to find three constants, c1, c2 and n0. Okay, so we should be able to find three constants, c1, c2 and n0, in such a way that if we take this function fn, we should be able to sandwich our fn into two functions, c1 multiplied by gn and the c2 multiplied by gn. Okay, and all of them should be non-negative. Okay, and this should be true for all the values of n, okay, which are greater than or equal to n0. Okay, so that's what we mean by this set theta gn. Okay, for example, if my gn is say n square, okay, then the question is whether function fn, I'll call it say n square, does it belong to theta gn? It does, because I can have the values for c1 equal to 1, c2 equal to 1 and n0 equal to say 0. Okay, for these values the function fn, which is n square, meets the criteria for belonging to theta gn. Okay, so what is actually happening is that if you try to visualize this on a graph, okay, if this is my n and here I represent the function on y-axis, if let's say this is my function, this is how my function say fn looks like. Okay, what we are saying is that there exists a function gn which can bind it from below as well as bind it from above. Okay, so we are saying that this is c1 gn and this is c2 gn, and in between I can fit in my fn. Okay, and it's not necessary that it should happen right from n equal to 0, it should happen after certain interval. Okay, so that's where my n0 comes in picture. So before n0 what happens is not important, there can be any relation between these, but once you cross n0, after that this particular relation, it should hold, that fn is sandwiched between c1 gn and c2 gn, and all of them are non-negative. Okay, so let's take one simple example. Okay, so in this case my gn is going to be n cube and my fn is, let's say, n cube plus 5n plus 2. Okay, first let's just try to build a table. Okay, so various values of n, what is the value of fn? So if n is 0, 1, 2, 3, 4, 5, and let me put what is the value of, in this case, fn. So for n equal to 0, my fn is going to be 0 plus 0 plus 2, it will be 2 fine. And for n equal to 1, it will be 1 plus 5 plus 2, so it will be 8. For n equal to 2, it will be 8 plus 10 plus 2, so it will be 20. For n equal to 3, it will be 27 plus 15 plus 2, so that would come out to be 44. For n equal to 4, it will be 64 plus 20 plus 2, that would come out to be 86. And for n equal to 5, it will be 125 plus 25 plus 2, that would be 152. Okay, so that's my fn. Okay, and now I will just write what is the value of gn. Okay, so 0 cube is 0, 1 cube is 1, 2 cube is 8, 3 cube is 27, 4 cube is 64, and 5 cube is 125. Okay, so now question is, can I find out the value of C1 such that my C1 GN is always less than or equal to Fn. So for example, if I take C1 equal to 1, then I'm sort of able to satisfy this requirement. So in that case, it is still 0, 1, 8, 27, 64, 125. Okay, so my C1 is equal to 1. Okay, and what will be the function in that case? So just think about it. So if I talk about Fn minus C1 Gn, what is the result? The resulting function is actually 5n plus 2. That's the resulting function. Okay, and let's take say C2 Gn, and in this case I'm going to have value of C2 as 4. Okay, so I'm going to multiply Gn by 4. Okay, so 0 multiplied by 4 is still 0, 1 multiplied by 4 is 4, 8 multiplied by 4 is 32, 27 multiplied by 4 will be 108, 64 multiplied by 4 will be 256, and 125 multiplied by 4 will be 500. Okay, so you can observe that C2Gn is always greater than or equal to Fn after you cross the barrier of 0, or after you cross the barrier of 2. Okay, so after this point it is happening. Okay, so if I write C2Gn minus Fn, the resulting function is actually 3n cube minus 5n minus 2. Okay, you can notice that for the values of n greater than 0, both these functions they are so for values greater than say 2, both these functions are increasing functions. So what is going to happen is our Fn can be effectively sandwiched between n cube and 4n cube, and that's why we are going to say that n cube is asymptotically tight bound for Fn, which is n cube plus 5n plus 2. Okay, so you can notice that when finding out the asymptotically tight bound, we can sort of ignore the terms which are of the lower polynomial powers. Okay, so given a function which might be representing the running time of an algorithm, the asymptotically tight bound will correspond to the most significant term. Okay, so the most dominating term, and it doesn't matter what is the constant associated with that particular term. So if it is 5n cube, 20n cube, 100n cube, still the asymptotically tight bound would correspond to the most dominating part of your function. Okay, so that's the way the theta notation works. So actually theta notation represents a set, but when we typically use the theta notation in algorithm analysis, we are going to say something like this, that function fn is equal to theta gn. Okay, so this is actually abuse of the notation. Strictly speaking, fn belongs to theta gn, but we will typically use the notation equal to. So even if we use the notation equal to, don't forget the underlying meaning. We are still saying that a function belongs to a particular set. Okay, so after this we'll talk about the notations of big O and big omega.